not every physical system that is governed by linear equations obtained from straight line graphs. Some physical systems behave in a way that is not linear. If we carry out a process, if we carry out a test on a physical system and we obtain a table, and after we plot it, we don't get a straight line, then we can't apply all we've been saying to such a physical system. What it means is that it is not every physical system that is governed by such linear equations. If an equation is not linear, then the line of best fit from the graph that led to it would not be a straight line. What other shapes could lines of best fit have apart from straight lines? That takes us to lesson number 8, and that is non-linear graph. Please follow me as I develop it. This is example number 3 on how to sketch an equation on a Cartesian plane. For this third example, let us use this table. This is a table I believe you have seen before. Did you also see this equation corresponding to this table? Yes, I believe you did. Y is equal to x to the power 2 minus 3. This equation is what we want to sketch on this Cartesian space. This equation is a summary of this table. Let us see whether every table when plotted or every equation when plotted produces a straight line Cartesian system. Already, the two axes have been calibrated accordingly. All the values of x are positive, but one value of y is negative. Please, before we proceed, confirm that all these values in the table conform to this x to the power 2 minus 3. That is, if x is 1, put 1 here. 1 to the power 2 is 1. 1 minus 3 is equal to minus 2. Do the same thing for the remaining pairs of values. Now, let's continue. Like I said earlier, the two axes have been calibrated accordingly. I believe that you could have done the same thing that was done here. It is not compulsory that 5, 10, 15, 20, 25 is the system of calibrating this y-axis. Choose your own that is convenient for you. But in this case, we have it like this. The same thing applicable to this x-axis. It is not compulsory that 1, 2, 3, 4, 5, 6, and so on is the calibration. Calibrate it also according to your convenience, but be sure that there is no error in the process. Having said that, please permit me to use this already made Cartesian space to plot this table, and afterwards we compare the shape of what we get with what we've got before in the past two examples, in the former two examples. First, we get the spatial points of intersection between x and y in this space. Let us see. This is an array of the spatial points of intersection here, 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 and here. What do you observe with respect to this arrangement of spatial points of intersection? Are they straight? Do you think they are straight like the former examples? You can judge by yourself. What I'm seeing here is not a straight arrangement. Anyway, let us not conclude until we have gotten the line of best fit. Before then, let us see how we got these partial points of intersection. First, we look at the values on the table. This 1 corresponding to x is here. This dot corresponds to 1. And 1 produced -2 as value of y. That means that if it is 1 here, it must be -2 on the y-axis. What is -2? From here to here is -5. Midway is -2.5. Therefore, a short distance before the midway corresponds to -2. Therefore, this point is -2. Therefore, -2 for y is paired with 1 for x. The two of them met here. When 1 comes out and -2 comes out, the two of them meet here. That is how we got this first point of a intersection. What about these two against 1? See 2 here. What is 1 for y? Let's try to get by estimation the position for 1. From here to here is 5. Therefore, if we're looking for the place to locate 1, it is 1 out of the 5 units from here to here. That is approximately here. Therefore, this is a position for 1. This is the 1 against 2 on the x-axis. This is 2 on the x-axis. Therefore, 2 comes out, 1 comes out. They both meet here. This is how we got this, or how I got this as the point of intersection between 2 and 1. What about when x is 3? See x being 3 here. That corresponds to y being 6. 6 is not marked on this axis. What we see marked is 5. It is this position that is corresponding to 6, just a short distance after 5. By the same procedure, I was able to get here as a place to locate the 6, the procedure of approximation. Therefore, when 6 comes out and 3 also comes out, they both meet here. This is why this place is the special point of intersection between 3 and 6. The same thing is applicable to 4 against 13, 5 against 22. Now, let us see how to get the line of best fit. Through a freehand sketch, this is the line of best fit. And like before, I ask again, what do you think about this line of best fit? Is it straight? No is the answer. What does that tell you? At least among other things, you should learn that not every graph is straight. Watch it. Instead of being a straight line, it is a curve. Before now, we got 2 other examples in which the Cartesian sketches were straight lines. Don't forget also that in the tables corresponding to those sketches, we observed one important thing, and what is that? The changes in the variables were constant. As x was changing, it was changing with a fixed amount from the start to the end. And as y was changing too, it was changing with a constant amount from the start to the end. But look at this one. Though x is changing regularly from 1 to 2 to 3 to 4 to 5, y is not doing the same. From -2 to 1, what is the increase? From -2 to 1, the increase is 3. That is 3 increased over this -2 to make 1. From 1 to 6, the increase is 5, no longer 3. From 6 to 13, the increase is 7. And then from 13 to 22, the increase is 9. Imagine here an increase of 3, an increase of 5, increase of 7, increase of 9. The increase is not constant. This is why we don't have a straight line. Anytime you have a table of this kind, which kind? A kind of table in which the values of the dependent variable are not changing with a constant value or amount, just to be sure that most likely what you're going to get is not a straight line plot. Anyway, you have seen an example with this one. Other examples which perhaps you will see in the course of time will make you understand that this is a fact. It is not every table in which the dependent variable keeps changing with non-constant amounts that we shall derive from a sketch that is not a straight line. It is a table in which the dependent variable keeps rising with an increasing amount, like this one. From here to here, 3. From here to here, 5. From here to here, 7. From here to here, 9. The increase keeps rising. If, for instance, from here to here is 3, and from here to here is 2, and here to here is 5, in that manner that fluctuates, we may not say that the sketch you're going to get from such a trend will be non-straight sketch. But just know it that the increase is not constant. Instead, the change according to y is increasing from the smallest to the highest values without anything called fluctuation. This is a precursor to the fact that in the end, what we get is a curve and not a straight sketch. What does this curve tell you about the way this x and y relate with each other? In the earlier times, the straight line told us that x and y were relating at a constant rate. But this curve tells us that x and y do not relate at a constant rate. If they don't relate at a constant rate, what it means is that it is either x is rising more rapidly or y is rising more rapidly. Let us see which one is rising more rapidly. That this keeps changing by 1 each time. I mean, x keeps changing by 1 each time, which is a constant change, compared to this y changing from 3 to 5 to 7 to 9, shows that it is y that is rising more rapidly. Therefore, as x rises uniformly, y rises non-uniformly. This is shown in this curve. In the end, the curve began to move more rapidly upwards than towards x. This is an indication that y is rising more rapidly than x. This is going to serve as an example to all other kinds of examples you're going to see in the future that are not straight line Cartesian sketches.